Okay, welcome to class. We'll do the reading quiz in just a second, so if you want to be logging on with your clickers while I talk about the homework, go ahead and get started on that. So the extra credit homework and the makeup for clicker points is as follows. If you haven't seen it, we made an announcement. It's like 3 announcements back on the 22nd. Here I describe how it's going to work. So as of last time I checked on total number of clicker points possible, there was something like 93. That's going to increase a little bit as we go the rest of the semester. It'll be somewhere around 100 points by the end of the semester, I'm guessing. Here's what we're going to do. You can make up 50% of your missing points, right? So if you got, 30 points right now out of 93, you can make up another 30, points or so, right? How you'll do that is by doing additional HHI calculations. We'll give you 5 points per, right? So in the comments, most people have been doing this, but you can just sign up, right? If you want 2, if you want 4, all I'm going to do is I'll see how many you've listed there. I'm going to grab your student ID number, and in the Excel sheet, I'm just going to start pasting these things, right? If we run out of room, we will generate some more. There's plenty of stuff that we have to work on, so that's not a problem. When you're ready to start working on this, just be aware that it takes maybe 5 minutes to calculate each one of these. It's actually a pretty small time commitment to do it. 5, 10 at the most, right, to do each one. And the more you do, the faster you'll get. But let's say that you're ready to report it. The best way to do it, since we're having multiple people test every score to make sure that you guys calculate them correctly, is when you're ready, like here's an example of somebody who's done it right. Student, this student over here, the 811 student, they listed all theirs. The student on the right, we calculate and list theirs, and we can compare and see if they're getting pretty close to the same thing or not, right? So don't paste them on top of each other. Paste them side by side, roughly. It doesn't matter if the countries don't line up exactly. Just put them both in the same spreadsheet, right? You have until December 15th to get these done. The final's on, I think, the 12th. I'll confirm on that. I think it's the 12th. So this will be a few days after. Right around then is when we have the final graded and when I'm actually getting ready to put final grades in. So we have to have any extra credit or makeup or, anything like that done by that point. Any questions on doing this? Yeah, Arthur?
If you ask for too many to actually get the full credit because you're going to only get 50%, will you yourself round it down, or do you have to change it?
No, I'm gonna manually go through these when we go to tally them up. What I'm gonna do is I'll see how many you signed up for. I'll see how many got turned in, how many were correct. Brendan's calculating that for us, and then I'll manually give you the clicker points for that. So, and I'll round up, right, to give you more points back. Other questions about this? If it's at all tricky, just shoot Brennan an email. He's listed on the announcement with his email. It's pretty straightforward. After you've done one, it's actually really easy to do them. Any other questions I can answer about this? Yeah.
So how many clicker points total were there in the semester?
Well, I don't know because it depends on how many we get through by the end of the semester. There should be somewhere around 100, but that will change. As of right now, I think there's 93 that you potentially could have gotten in class, and you can earn back half of those, half the missing points. Yeah.
Was that going to be like a separate page from the one that we used to get like homework?
Yeah, so I have, we know where the cutoff was for homework versus the other ones. So the first one that you do was for the homework, basically, to give you your points on the homework. And then all the ones after will be for the clicker makeup. Yeah, Josh?
It's worth it, like, isn't it that if you get over 70% correct?
Yeah, absolutely, yeah. Okay, any other questions I can answer about anything? Sorry, what's that?
You get over 70%, what?
So, as I mentioned earlier in the semester, I don't expect you to get every single clicker question in class right. I expect to use clickers just to keep people engaged, to make sure that you come to class, that you're working, that you're doing the reading. I don't expect you to get everything right. So if let's say there was 100 points possible, I'll probably make the A cutoff like 100% out of maybe 70 of those points, right? I haven't drawn the line there yet. I have for civils already because they're done for the semester, but it's typically somewhere around there. Okay? All right, one last thing to note is Google Docs doesn't actually let us make like infinitely large spreadsheets, as we found out. So right here, basically, if you have any data sets that are below the year 2000 titanium, then you actually have to post your answers in this second spreadsheet. We actually maxed out the Google machine, so. Okay. All right, if you have other questions, feel free to shoot me an email and ask about it. And again, if you want to sign up for them, on this announcement where we talk about makeup for clicker points, you can just post a comment, and as soon as I see it, I'll make your assignment on there. Okay, let's start with our reading quiz for today. Okay, the first question says, which of these is true about insulators and semiconductors? A, they have the same Fermi energy. B, insulators have a much narrower band gap than semiconductors. C, semiconductors have a much narrower band gap than insulators. Or D, they both behave like metals with regard to band gap. Okay, we're going to move on to the next question. Okay, definitely C on that one. All right, how about this one? The larger the band gap, E sub G, A, the higher the conductivity at any given temperature, B, the lower the probability of electron excitation to the conduction band, or C, the hotter the material. Okay, on to the next question. Okay, good. Okay, in semiconductors, a positively charged particle that moves in the opposite direction of electrons is called A, a positron, B, a current particle, C, a hole, or D, a Bose-Einstein condensate. Okay, moving on to the next one. Okay, it is a hole, so 2/3 people got that right. Okay. All right, we're in chapter 12 now. We're going to leave off the very last bit of chapter 11, the kinetics part that we didn't get to for the sake of time. We're going to dive into chapter 12. Chapter 12 is on the electronic properties of materials. And, you know, there's some uniquely interesting things about the electronic properties. Things like piezoelectrics. Anybody use piezoelectrics in your labs or in your research? Anybody use these? I'll bet you use them and don't even realize it, right? Most speakers, anything that vibrates or makes noise, most of these have piezoelectrics in them. Your phone, when it vibrates, that's a piezoelectric. We're going to talk about what is it about the fundamental, at the crystal structure level, that couples an electronic signal with a mechanical strain, right? And then if you apply that signal in a fast alternating fashion, then that strain becomes a vibration, right? We use these all over the place. We'll talk about how those come to be, right? To start with today, we're going to learn about electrical conductivity. And what's interesting is that we've already talked about mass transport and heat transport. We're going to see that electrical transport of these electrons or holes, can actually be thought of in much the same way, right? It has a driving force, has a constant proportionality. We're going to differentiate between what's the total resistance of some object and the intrinsic materials property, which is the electronic resistivity, right? We'll calculate heat change as it passes through a material. We're going to introduce band diagrams and use band diagrams to introduce the idea of band gaps. And once we know what a band gap is, we'll use that to differentiate metals, insulators, semiconductors. That's really at the heart of today's lesson is getting towards band gaps. If we have time, we'll describe occupancy of electrons around the band gap with the Fermi-Dirac distribution, and maybe even talk about mobility of these carriers. So let's talk about electrical transport, right? If you're like me and spent your Thanksgiving break trying to sew a ludicrous Christmas sweater where my thread was stainless steel that conducts the current, I should have reviewed this lesson before I did this. because it was not high enough conductivity thread. It was too resistive, and I spent many sad hours making a sweater that doesn't work. It makes me really, really sad. But we haven't given up. We just have to plumb it with copper wire, which is not as awesome as conductive thread, but it's going to work. So, why was it too resistive? Where did I go wrong in my conductive thread in my Christmas sweater, right? Well, let's start with mass transport. When we talked about mass transport, Fick's first law says the flux of atoms, they're going to travel down the concentration gradient, so there's our driving force, dc dx. The constant of proportionality that tells me how fast they're going to move down that gradient is the diffusion coefficient, capital D there, right? When we talked about the flux of heat, J sub Q, we wrote it as Q before, but Q sometimes is just energy. J sub Q is the flux of this energy, right? It's the temperature gradient that's our driving force. If you have a hot spot, right, then it's going to move away from that hot spot, down that gradient, right? And the constant of proportionality in that case was the thermal conductivity, right? So with electrical conduction, it's going to be very similar, right? What is actually flux? Flux is always something per unit area per unit time. So let's start with current. Electrical current, that has the units of amperes, right, per meter squared, right? And an amp of something is coulombs per second. So current, I, that's really equal to the number of electrons, right, coulombs, per meter squared per time. So that's a flux. That's a number of something per area per time, right? So current is going to be our flux. How much electrons are traveling through your material, right, per area per time. All right, now what's the driving force? How do you make electrons, or conversely holes, which we'll talk about what holes are a little bit later. How do you make electrons move in a material? And you guys have seen this. You take a 9-volt battery, right? If I hook one end of my 9-volt battery up to one wire, right, and hook the other one at the other end, I'm going to produce a current through that wire, right? So what is it about the battery that makes that happen? The battery is a voltage, it's a potential, right? And if you take that potential and you divide it by some distance, you create an electric field, right? The closer you bring those leads together, the bigger the electric field, and therefore the larger the driving force. And the further apart that you take those wires, the bigger that X is, the further apart is, right? So the electric field E, it's going to be equal to the negative d phi over dx, where d phi, that's our potential. We usually write phi just as V, right? That's the change in voltage. So again, if that's a 9-volt battery, that's 9 volts divided by whatever separation distance is when you hook this thing up. A centimeter, a foot, a mile, whatever it is, right? So if you have your leads really, really far apart on something, then you have a smaller electric field than if you put them really close to one another. If you put them close to each other, you have a bigger driving force because this is our driving force, right? All right, so we have our current, we have the driving force. What is the constant of proportionality, right? We call this the electrical conductivity. It's not the thermal conductivity now. We use the unit sigma, right, the Greek letter sigma, and this has units of Siemens per meter or inverse ohms per meter, or sometimes they write mhos per meter. Mo because that's ohm spelled backwards, right? I didn't come up with this. Someone else did, right? So all of a sudden, this is now kind of starting to look like things that you've seen before, right? In high school, you probably saw V equals IR, right? The voltage that you get, or rather, if you provide a voltage and you know what the resistance of your circuit is, you could calculate the current that will go through it. This is starting to look like that, because here you've got current, right? This would be like our I. We have resistivity, which is going to be kind of similar, or that's conductivity, that's going to be related to our resistivity. And then you've got E, which is related to the voltage, right? So we're getting there, it's close to it, right? So V over I is our current. Let's see. Oftentimes it's more useful to think of electrical conductivity in terms of resistivity, right? The steel threads that I was using in my sweater over the weekend, they actually tell you that it should be, I think it's like 40 ohms per linear foot of the thread, right? So for every foot that you do this, you're adding on another 40 ohms, and you can do that to figure out how much current then is going to be lost in your wire versus in your LED or whatever your device is, right? This is what I should have looked up before I made this stupid thing, right? So instead of conductivity, it's useful to talk about electrical resistivity. Now resistivity, that's a fundamental materials property, meaning it doesn't matter how big or small the object is, the resistivity is the resistivity, right? So for example, in the wire, when they say 48 ohms per meter, right, or per foot of the thread, that's useful because then if I have 2 miles of the thread, I could add up and I could figure out how much the total resistance is because it's the resistivity, right? So that's the difference between this, the Greek letter rho, which is for resistivity, and capital R, which is for total resistance, right? Basically, you need to use the geometry of your sample to go from rho to R. Any questions so far? Yeah, Rosa?
What exactly does it mean when it says the geometry of the sample?
I'll show you in just a second. We have an example I'll get to in just 1 second. So let me come back to that. Other questions I can answer so far about electrical conductivity, electrical resistivity. Now, fortunately, we have both electrical conductivity and resistivity, and they're just an inversely related thing, right? So whereas electrical conductivity was 1 over ohms per meter, when you take that and you flip it, 1 over that, then the resistivity just has units of ohm meter, right? Not 1 over that, okay? So there's 1 over the other. Okay, so how do you go from the material's property, which is electrical resistivity, to the resistance? Because when you did your electrical engineering class and you used a bunch of resistors, what you really cared about was just the resistance between the two wires, right? Whatever that resistor was doing, you didn't care about the resistivity of it. You just cared about the total resistance. So here's how you calculate it. The resistivity is equal to the total resistance times the cross-sectional area divided by the length. Or, more useful, the total resistance of your resistor is going to be equal to the electrical resistivity times the length divided by the cross-sectional area. Okay? And so between the top and the bottom, all we've done is we've solved for resistivity on the top one and total resistance on the bottom one. Oftentimes, it's more useful to consider the total resistance. That's what I should have cared about. I knew that the resistivity of that steel wire wasn't that high, but I didn't realize that by running it all the way through the flipping sweater that I was going to build up a pretty large total resistance, and therefore my current that would pass through my sweater was not enough to make it do the things I wanted to do to spread holiday cheer. Right? So, if you wanted more, let's say I wanted to fix my problem, right? Let's say I wanted to take the sweater as it is, right? And I wanted to make it work, and I didn't want to run copper wire through it, which is what I did. What could I have done? Based off of this geometry, maybe turn to a neighbor and discuss what would be an option to take the sweater and modify it in some way to keep the thread and still increase my current by reducing total resistance. What should I do? Okay, any ideas? I'm secretly just consulting. I'm having you guys solve my problem. No, Rob, what would you do?
I make it wider, so either braid it or I twist a couple together.
Okay, yeah. Basically, he says make it wider, right? So the current's passing this way. Think of it, I don't know if you guys have taken Arne Stolp's ECE class, but he does a great job of describing this. The flow of water right through pipes can be thought of in a very similar way to the flow of electrons through wires, right? So if you want more flow of water, what do? You use a larger diameter pipe, right? If you want, for a given pressure, right? We can do the same thing here. Instead of having a small cross-sectional area, if we increase our cross-sectional area, we should, right, if this goes up, then my total resistance would go down. And then if you recall that V equals IR, then for a given voltage, right, my power supply on this thing, if this goes down, then my current should go up. So yeah, that's one way you can do it. How would you do it? I think you said braid it. Before I put these wires on, I could have braided or twisted a few of them together and then sewed with that. Absolutely. Josh?
You could copy your design again, one lower and then parallel.
Yeah, that's another thing. So I'm not going to get into that in this class. If you take an ECE, you realize that there's ways to keep constant voltage or constant current by connecting things either in parallel or series. I could have redesigned it in that way. I could have separated my circuit and done one power supply for this side. Anything like that to reduce the overall length, right? Reducing length would have reduced resistance, right? If L goes down, then R also goes down. Anything else we could have done? Anybody have a clever idea? One that they suggested online as I was debugging this is to actually sew right over where you sewed before, right? And then just connect it right up, which is basically what Rob said. It's twisting a couple together. But we didn't do that. We did something else to fix ours. Okay, this makes sense though. The relationship between resistivity, which is the material's property, and the total resistance, which is oftentimes what we design around and care about. Straightforward? Okay. So this also explains, the iron wire that we did earlier in the semester. When I first came up with that iron wire demo, I went to Home Depot and I bought some iron wire, but it was really thick gauge. What was it? I think it was like 12 gauge. Yeah, 12 gauge wire. And if you look at this gauge chart, 12 gauge wire in inches, that's 1/10 of an inch. It was actually pretty thick wire. It was like for, I don't know what they use, like tying up fences or something. And that was way too thick. And so what happens, when I went to set that up with a really big cross-sectional area with that big thick gauge, that meant my resistance went way down, right? So when I hook this thing up and I start passing current through it, as I start to crank that dial to increase the voltage, all of a sudden, because this is not that resistive, because it's such a big cross-sectional area, it's telling Ohm's law is predicting that it can have a higher and higher current, and I actually blew a whole bunch of circuit breakers, right? Because it started drawing more current. It was basically acting like a short. It's as if you were to stick a fork in your light socket. You just short it out. So for me to fix that, what I ultimately had to do is go to Joann's. Just been all about the sewing this semester. Go to Joann's and buy their very thin iron gauge, right? Much, much thinner. I think I bought like a 20 gauge or something. And 20 gauge is clear down here at like 0.035, so massively thinner. And when I did that, now the current through it is small enough that I don't trip breakers when I do that demo, right? So you can actually calculate, we're going to do this for a question real quick. You can calculate as a rough approximate how much heat gets generated when you send electrons through a circuit, right? So we hooked up a battery in this room, right? This side to that side. And if you guys were electrons, you feel the electric field and you want to move opposite the electric field's direction, right? So the electrons are going to be moving, and what's going to happen is that as you're moving, you're going to collide into other atoms. And as you do so, you're going to impart a little bit of energy. We call this process joule heating. Joule heating is when you pass a current through something, it just heats up a little bit. If you pass a big current through something, it heats up a lot, right? The old incandescent light bulbs, the filament was quite small, right? So the joule heating was the same amount of current was passing through your circuit, but right where that wire was, since the filament is a small cross-sectional area, the resistance of that piece of tungsten was actually quite large. And so the amount of heat that gets generated is proportional to the current squared times R times T. You can generate actually quite a bit of heat. You can make these things glow white hot instantaneously. So in your homes, you could actually be concerned, what if my electrician who wired my house wired it so I'm going to generate too much heat that it's going to melt the casings on those wires, catch things on fire, right? So before that, they used copper in homes in the 50s, and before that actually, they would use aluminum. But one of the problems is that it would be a little bit too resistive, and it would either melt the wire or otherwise generate too much heat, right? So if you want to if you want to be sure on whatever you're designing, like say on my sweater, I want to know, is all the heat that I'm generating going to cause this sweater to catch on fire, right? We can do a ballpark estimate, right? You would say, all right, Q, the amount of heat that I'm generating is going to be I squared times R times T the time. If you plug those in, you're going to get units of energy, right? All right, let's keep going. Let's do our next question that says the following then. How much heat would be generated by passing 15 amps? By the way, what's a home good for? The circuit breakers in your home, what are they rated to? How many amps? Anybody know this? 25 or 30. It depends on your circuit breaker, but those are typical numbers, 25 or 30 amps. So 15 amps is something that absolutely your power supply could give, right? It says that's passed through a long rectangular copper sample that has dimensions of 3 millimeters by 4 millimeters by 10 millimeters. Let's assume that it's sort of matchstick shaped. So you're passing the current along this long direction, right? So you've got 3 by 4 by 10, right? That's your dimensions. And you send it there for 1 minute. Assume that this copper has a constant electrical resistivity. What do I mean by constant? Meaning that as you heat it up, that the temperature's not affecting the electrical conductivity very much. That's not a fair assumption. It is going to change, but we're going to say for this demo, it's not going to change a lot. So you've got the electrical resistivity in nano-ohm meters. So I'd like you to calculate and round it to the millijoule, how much heat is generated. So recall that Q, the amount of heat that we generate, is I squared times R times T, our time, and that R, the total resistance, is equal to the resistivity times the length over the cross-sectional area. And then just watch your units. And then again, with your units, recall that 1 ohm, that's equal to a joule per second times amp squared.
No, it's
Okay, another 30 seconds. Phone a friend if you need. Okay, we're gonna wrap this one up. Answers in. Everybody. Okay, we're gonna end. Frantic answers still coming in. I feel bad when they're still rising. Okay, we're gonna end it though. What do people get? So yeah, those look great. So vast majority of people, I got somewhere around 188 millijoules. So these are all going to be correct answers probably, and maybe 10, 15% were off somewhere. So when you do this, the things that can go wrong is really just units on this, right? So with resistivity, when I come up with, I get the total resistance is equal to 1.398 times 10 to the negative fifth. And that's ohms. And then all you have to remember that 1 ohm is equal to a joule per second times amp squared to do the rest of this calculation. Okay, so again, I end up with 0.1887 joules, or in other words, that's equal to 188.7 millijoules. Okay, any questions on this? Straightforward. This is just an approximation. This Q equals I squared RT. It's actually proportional to that, but it's not a bad place to start, right? This is not a bad first estimate. Okay. We could take this a step further. We could say, okay, if the copper was initially at room temperature when you started this experiment, what would be the final temperature of the copper if it has a specific heat, which is related to it's basically the heat capacity divided by its density, and a density given, right? Give the answer in degrees Celsius, rounding it to the nearest degree. So here's how we're going to set this up. We'll say that heat capacity, Cp, that's equal to Q that goes in to make some mass of material change some temperature, right? That's what Cp is. So in this case, we know what Q is, right? You've got Q from before. You don't know how much mass there is, but you are given the density, so you know the volume of this thing. The volume is 4 times 3 times 10. Turn that into millimeters cubed, right? You could use density to turn that into a mass, right? You know what this value is, so all you then have to do is figure out what's your delta T. If you start at 25 degrees C, how many degrees do you pick up? So go ahead and give that a shot. And then one thing to watch for to make sure is this specific heat, that's in joules per kilogram Kelvin, and this density is in grams per centimeter cubed. So you'll want to make sure that you have kilograms on both sides, or convert this to grams. Either way, watch for mass. Okay, another 30 seconds or so on this one. Okay, answers in. Looks like most people are. Gonna wrap this one up. Okay. By the way, these are the sort of things. This is a single equation with one conversion. You'll want to make sure that you can do these faster. I think that's what's killing a lot of people on tests, like just doing these conversions. If that's what it takes to practice going through those, that's something you should be able to do in just a minute or two, not 5 or 10. Okay, so the final temperature should be around 25.05. That's correct. That one's correct. These I'm not sure. This one's right. So looks like 4 out of 5 people roughly got this correct. Okay, so things that can go wrong here are really just units, right? How do you turn that into mass? You have to use density, right? So this is going to be 120. That's 120 millimeters cubed, right? But when we turn that into a mass, you have to recall that right now the density is given in it's in grams per centimeter cubed. It's going to be more useful for us to turn that into kilograms per meter cubed. So if we multiply that, it's just 8933 kilograms per meter cubed. Now we're almost there, except that the millimeters cubed won't cancel with the meters cubed, so you need to make that correction. So the way you can do it is you just recall that, okay, there is 1,000 millimeters, right? 1,000 millimeters in 1 meter. And then we're talking about things cubed, so you have to cube that whole thing, right? So that'll give you your mass. You can plug into there. And then your units over here are going to be joules per kilogram Kelvin, so your kilograms will cancel. You make sure that you use the energy above that was not in millijoules, but in joules, right? So that the joules cancel. And you'll solve for your delta T. And I get that it's 0.045. 0.045. degrees C. So your final temperature must be that much hotter, 25.045 degrees C. So this is an interesting calculation because it tells us this wire, which is getting 15 amps of current, which is quite a lot, right? It's quite a bit of current, and it's not like it's a huge, big, thick wire. It's about like matchstick dimensions. Even though you run it with that pretty big current of 15 amps for a full minute, it's negligible heat gain, right? Almost nothing, right? So that's why copper makes such a great material to wire electronics with, because of its extremely low resistivity. That means that you don't get a big voltage drop and experience a problem I ran into, right? Where I had such a big voltage drop across my thread that my components didn't have the voltage that they needed to operate. Plus, you're not going to generate any heat, right? If we take a material that has a higher resistivity, then your resistance goes up. If your resistance goes up, you generate more energy, right? If you have more heat being generated, then your object's going to heat up more, right? So copper is just great for this. We could repeat this calculation for silver, but we don't have time. You could calculate it with steel, right, and see how much worse you do. You're going to find that copper, though, is one of these great materials because of its incredibly low conductivity. Incredibly low resistivity, high conductivity, electrical conductivity. It makes great for wiring materials, right? You have other materials, right? Say something like nichrome. Nichrome they use for heating elements, right? So it's not the only thing they use, but they have used it in the past, like for the spiral heating elements on your stove at home. They pass a current through those, but this time it's so highly resistive that the heat that it generates is pretty large, right? And it's intentionally so. So it'd be interesting, you could calculate what would be the difference for nichrome. How much more heat would you generate, okay? Okay, electrical conductivity, or conversely electrical resistivity, it varies over 28 orders of magnitude. To my knowledge, that is the biggest variation in any single material's property, period, right? Meaning, any other property, whether it's strength or whether it's, thermal conductivity or whatever it is, I can't think of anything that varies over such a large range. 28 orders of magnitude. That's like billions times billions. That would only get you to 18. Times it by a third billion, and it's like a billion cubed, right? That's huge orders of magnitude that this thing can change, right? So you've got things that are just the absolute worst imaginable conductors of electricity. Things like foams that would be up here, right? Glass, rubbers up here, just terrible. And then if you go to the bottom, very, very low resistivities, these are your good conductors. You've got copper and aluminum, right? Gold, some of these materials, way, way down there. So this type of chart, by the way, is called an Ashby chart. They're useful in the literature because they plot different things and they take classes of materials and do big clouds for them, right? So even though there's lots of different grades of aluminum alloys, they all sort of lie in this range. They can be very expensive, they can be not that expensive, but they've all got the same electrical conductivity, at least in this log plot, right? You don't see a big change there. Whereas other things maybe pay for a premium in terms of it, right? And it's not a great show here, but these sort of plots are useful here. In case this is the x-axis is cost, but you could have it be anything else, right? So if you wanted to take two properties, you wanted to get the best conductor and the lightest weight, then you could plot it against, density, for example. Okay, so that's an Ashby plot. Yeah, question, Rob?
Sorry, just kind of an interesting thing. Could you relate that to I forgot the name of it, but the extra credit thing you wanted to do, where we're talking about how
yeah, HHI. HHI is not related because it's not a material property. It's a for some component, right? So for a commodity, I guess I should say.
Yeah.
But in that case, we wanted the highest performance, right? Which I scaled that with marker size. Here, marker size is not performance.
Yeah.
Here, marker size is basically saying what values do these things exist at. And then for me, I wanted low concentration and high abundance, which was some region plot.
Well, what I mean is that could you, based on the width of each of these clouds, could you determine sort of like the narrowness of the market? Because for really, really narrow fields, like for example, copper is a very small bubble, and what I'd imagine that means is that it's a highly regulated market, meaning that it's a pretty regulated cost. So it all comes from one source.
Yeah, actually probably could correlate it. Something that we built, this is for thermoelectrics again, we can choose for the X and Y parameters. Let's say you want X to be electrical resistivity and Y you wanted this to be HHI. This allows you to generate plots. In this case, we're going to generate a plot. We're going to generate a plot where the Y is your HHI of production, X is your electrical resistivity, and then marker size scales with efficiency, right? So yeah, you can make these sort of plots that combine resource considerations with performance. It's not common though. It's sort of, I just did it a couple years ago, and I don't know people that are doing it otherwise. Okay. Okay, just some rules of thumbs. What do we expect for conductivity? Metals typically have electrical conductivity of around 10 to the 7 ohm meters. Semiconductors are 10 to the negative 6th all the way up to the 10 to the 4th. And then insulators are 10 to the negative 10 to the 10 to the negative 20 ohm meters, right? So those are some ballpark numbers to have for conductivity. Okay? Okay, we've got 5 minutes left. Let me use that time to introduce the notion of how bands form in materials. In the next class, we're going to describe, once we know how band gaps exist, what do we do with these band gaps? How do they help us understand materials? So it starts with your individual atom. If you have a single, let's say just a lone hydrogen atom, we can predict a lot about that thing. We know that it has 1 electron, 1 neutron, 1 proton, right? We know that we can give energy to its electron and make it occupy energy levels which are not currently occupied, right? So if you've got your nucleus and you've got these orbitals going around it, the electron is going to be at the lowest orbital, but if we give it some energy, we can make it temporarily go up to a higher orbital, further away, higher in energy, right? We can make it go up a couple, right? And then we can also know that it's going to eventually probably decay back down, right? So that's all fine. What happens when you bring more than one atom close together, though? It changes things, right? So, for example, if you've got your orbitals looking like this, this is for just a single atom, hydrogen or whatever else, right? The electron occupancy is going to be a single discrete value, right? And again, it can go up to the one above, it's going to fall back down. As soon as you start to bring multiple atoms together, bringing them close to one another so that these orbitals sort of would overlap, and that's the key word. If they start to overlap a little bit, you have to have a splitting of these orbitals, right? So instead of having 2 orbitals, they're both at the same level as before. Now they have to be slightly different in terms of energy, right? Our y-axis is energy, so one's slightly higher energy to fill, one is slightly lower. Any idea why? Why can't they both exist for the same volume of space with the exact same energy? That ring a bell? Yeah, Jeff? That's Pauli exclusion principle. Pauli exclusion principle says you cannot have electrons occupying the same volume of space with the same quantum numbers, basically. So the way that we fix that is you introduce a small, what's called band splitting, right? We form a band. We form our very first band. It's only got 2 orbitals, right? And this splitting is going to be very, very small if you only have 2 atoms. As you add more and more atoms, these things start to overlap more. Each one of these has to have its electron at that energy level, but it has to start getting split so they're not exactly at the same energy level. They're in the vicinity of it. And if you add more and more of these together, you start to form a legitimate band, right? So the band that forms now basically says, okay, you can put in your electrons anywhere in that region there. Those are all available states, but it has some thickness, right? Some thickness in terms of energy where you can place electrons. Any questions so far on the formation of bands? Yeah, Rosa?
So, like in the second level, I think it has is that where it splits off into the band? Is that the 2 energy levels from the first one, and only the second one is splitting on the second line?
They're both going to split. One will go up a little bit, one will go down a little bit, right? So if they were both here like this before, that's the 2 atoms lone, far apart. And when you bring them together, then they're going to split just a little bit. And as you add infinitely many atoms, as you go from individual atoms to now a solid, which has millions and billions of atoms, right? Then the splitting between this, excuse me. It's not working. The splitting in those levels gets very, very small. Okay? And that forms a band. Because you have bands, you can also have band gaps. So you can have regions, I'll just pick up here next time, it's actually not writing. But you can have regions that fill, and you have regions that don't fill, and then regions that fill again. So you've got this gap in energy between EV and EC where it is not allowed to occupy. Electrons cannot occupy that energy level, right? They either have to fill the ones below or gain energy and fill the ones above, but they can't exist in between. And that's the introduction to band gaps. We'll now use that next class to describe a lot of interesting physics.